Thanks so much, John. Thanks so much. I'm very grateful for the opportunity to present our research to you today. I'm also grateful to my co-authors, including a few in the room today, Dr. Chuck Medenjen and Phil Wernett. With the passing of the Great Lakes Fisheries Research Authorization Act in 2019, USGS, in consultation with the Fishery Commission and the Council of Lake Committees, initiated two new major studies to address key uncertainties in fisheries assessment science. In the common session presentations that follow mine today, you'll be hearing a lot about the fruits of this investment and also some of the spin-off projects that arose from that investment. My specific presentation focuses on high uncertainties around lake-wide estimates of round goby abundance. As round gobies became a very important prey item for many of the predators in the lakes, it became more and more important to index them accurately. And the indexing up to now has been done primarily using bottom trawls, which are widely considered to be biased low because of their inability to sample efficiently in the shallow water and rocky habitats preferred by round gobies during the sampling season. As an alternative to that, we developed what amounts to a new swept area method that draws on untethered robots called autonomous underwater vehicles, like the one you can see in the left-hand side of the slide there, combined with machine learning. So essentially what we've done is developed a new summer survey targeting round gobies in the habitats that they prefer for their reproduction and over summer activity. And that essentially amounts to the 0 to 50 meter depth zone. Within a given lake in a given sampling year, we've tried to target each of the sampling lakes, which we're so far targeting Michigan, Huron, and Ontario, with 30 10-kilometer transects that are shallow to deep transects, traversing the entire distribution of that 0 to 50 zone and hopefully to deeper water if our AUV battery life allows. Transect start locations are allocated randomly within statistical districts in proportion to the size of the statistical district, giving us a reasonably spatially balanced sample. And we're also trying to allocate those random starting points into areas that are primarily dominated either by coarse substrate or fine substrate. Once the transects are allocated, we essentially enter this process of our methodology where we fly the AUV from shallow to deep at a 1.75 meter altitude. And along that path, it's collecting overlapping color images the entire way. And the images are pretty high resolution. And the images are also georeferenced by a small inertial navigation system, essentially an underwater navigation system. So out of many thousands of images, we'll take non-overlapping ones. We will take our georeferenced images and essentially try to either manually or eventually with machines identify round gobies that are present. And once we've identified round gobies, we're in a position to summarize their numeric abundance. And because we also know their sizes, we can also estimate their weight. And so at an image-wise level, we're able to summarize both the numeric abundance and the weight of gobies present. And because we know the area of each image that we're collecting, we can relativize those to a measure of density. So the image-wise sampled densities are essentially the fundamental unit of our swept area method. And we extrapolate those up to the lake-wide level in a way very similar to the bottom trawl, where we take the sample density within sequential depth bins, and we weight that value by the area of that depth bin at a lake-wide level. And that's exactly how it's done in Lake Huron and Lake Michigan and in Lake Ontario to extrapolate out from the swept area method that is bottom trawling. The only difference here is that we've also incorporated coarse and fine substrate within each depth interval. And we're using a very simple sort of binary classification of substrate here. And we're using the Great Lakes Aquatic Habitat Framework substrate map for now to derive those for our extrapolation purposes. So we've done a huge amount of work over the last 5 years. I'm only going to be able to touch on some of the highlights here. But the first major accomplishment is that we've been able to successfully engineer robots that can essentially be put in the water in very bright, shallow water in Lake Huron, where we have massive photon flux, and in a single mission, get down to, in some cases, 100 meters water depth where you have full darkness, and collecting overlapping color images that are about 0.4 millimeters horizontal resolution along that whole path. That has been an important and difficult task. Rather than get into too much detail, I'd point you to this recent publication out of my lab to get all the sort of nitty-gritty details of the 2 generations of camera and robotic systems that we've been using for that. The 2 big points that I'd like to leave you with on this topic, though, are that in the 2024 sampling season, we finally got to a rate of interpretable images where that was quite high. So 83% of the images we collected that year were interpretable and usable for our downstream machine learning. And we had a pretty low rate of rejection. The other point I want to leave you with is that essentially the R&D phase of the hardware preparation is over for this. We're ready to deploy the same robot in a repeated way year after year to collect consistent data. And these things can fly just as well over sand as they can over rocky habitats. And the images look quite good. You can see in this series of images, there's a lot of evidence of mussels on the lake bed, but these are typical images that we're getting as of the 2024 sampling year. Another major accomplishment is that we've been able to automate the attribution of coarse versus fine substrate to whole images. So in the same exact images where we're quantifying round gobies, we're also able to quickly and efficiently attribute whether it's in a fine substrate class or one of these coarse classes. And we're able to do that with about 96% accuracy, which helps us when we're going to summarize our densities within these 2 substrate classes for later extrapolation. We have worked very hard on a challenging problem to automate the detection of a cryptic benthic fish in a visually complex environment. We've done that using sort of cutting edge machine learning approaches. The specific approach we're using is called You Only Look Once, YOLO, and we're using the version 8 of that algorithm. And this is an approach that puts a bounding box over around Goby. And we've found that the diagonal length of the bounding box is actually, here's the diagonal length of the bounding box on the y-axis. It correlates very tightly to fish total lengths. And so just by having a bounding box placed on around Goby gives us the ability to also use length-weight regression to arrive at that individual's weight, which of course gives us the ability to then tabulate it and summarize it at an image-wise level. Something that we were really, really careful and put a lot of effort into was to pick a very spatially balanced sample of training images and to prepare those images to essentially feed into the artificial intelligence systems so that those systems learned how to identify gobies in every physiographic, hydrographic condition that was present in the 3 survey lakes where we were working. So we have the very dark tan-stained waters of eastern Georgian Bay in there, as well as the extremely bright, calcium-rich waters of Lake Huron and the greenish-tinged waters of Ontario. So across all of those, we manually annotated and extensively QA/QC'd almost 70,000 images, and that became the basis for training our AI to do its job. And this is an example of an image with a high number of round gobies in it. The model outputs are these red bounding boxes. Each one has a probability that a goby is present, and the black boxes that the red ones are overlaying on top of are manually identified gobies. And so you can see pretty much we're getting about 80% accurate recovery of fish that are visible to the camera with our algorithm at this time. which again, I feel quite good about given the cryptic coloration and the challenge of this problem. Now, we have successfully applied this method with tweaks between 2020 and 2024. Lake Michigan was kind of our inaugural target lake, but you can see in 2020, and as I move through this, how we progressed through the lake system. What I do want to point you out to here, though, is that, so what I'm going to show you are sample densities within 5-meter depth bins. Typically when we do bottom trawling, when we show kind of our biggest, highest abundance, it's usually around 10 kilograms per hectare. If you just look at the scale of our legend here, that 10 kilograms per hectare fits within this sort of first smallest box. And in this survey, we were observing, in some cases, almost 1,000 kilograms per hectare sampled, in very patchy environments. So in 2020, we sampled Lake Michigan. 2021, we moved over to the U.S. side of Lake Huron during COVID. In 2022, we achieved our first sort of 3-lake effort, including the Canadian sides of both Huron and Ontario. And I thank the Ontario Ministry of Natural Resources and Forestry for sponsoring our travel over there, being our host. We were able to duplicate that sample again in 2023. And then in 2024, we focused our effort back in Michigan and Huron. When you tabulate these across all years, you can see some relatively sort of consistent patterns in high densities. And you can also see sort of the accumulated effort that has gone into this study, which is quite substantial. Now moving to the direct comparison of the Goby bot estimates to bottom trawl estimates. So essentially, this is a diagram showing time on the x-axis. This is the lake-wide estimate of biomass density on the y-axis. And the dotted lines at the bottom are, the orange line is for Lake Huron bottom trawl. The blue line is for Lake Michigan bottom trawl. And then the solid lines of the same colors are the Goby bot estimates. Now, rather than, I want to sort of advise you against trying to make inferences about trends here. Remember, we were tweaking our methods and our hardware between 2020 and 2024. But what I'd rather draw you to your eye towards is actually more like the magnitude of Gobies that we're indexing. So in some cases, we're indexing more than an order of magnitude greater around Goby densities than the bottom trawl. We are confident that we can replicate that year to year now and sort of begin to develop a trend data set that is reliable and is not prone to sort of methodological changes year to year. I also want to point out, though, that we put the Lake Ontario results on top of the Huron and Michigan ones. Lake Ontario calculates their lake-wide index slightly differently, and so we can't show their bottom trawl on the same chart and have it really make much sense. But when we calculate the Ontario lake-wide densities using the same methods as Michigan and Huron, which is essentially a 0 to 118 meter depth zone only, you can see that Ontario as a mesotrophic lake is expected to be more productive, and it appears to be that way. When we actually take Lake Ontario and compare it directly to the Lake Ontario bottom trawl from that lake using their consistent within lake methods, we're still seeing a large increase with the Goby bot based index versus the bottom trawl based index. So with all new methods, there's a lot of caveats, and this method certainly has its biases. Unlike the bottom trawl method, we are able to sample reasonably efficiently in hard substrate. However, we're still not sampling that efficiently in hard substrate. We recently had a microcosm experiment accepted in the Journal of Great Lakes Research, where we essentially seeded microcosms with known numbers of fish in a sandy bottom microcosm versus a single layer of clean cobble bottom. And when we had 2 manual observers count the fish that they could see in those different treatments, we found that in sand, we recover almost everything. The only thing, when we miss fish in sand, it's because gobies have a tendency to bury themselves in sand. When we miss fish in cobbles, it's because gobies have a tendency to hide really well, and that's their survival strategy. And so our efficiencies in cobble in this very simple experiment, without all the complexities of dry-seated mussel encrustation and attached algae and all these other things, is only about 55%. And there's a reasonably large confidence interval around that estimate. So even these index values being almost an order of magnitude higher than the bottom trawl, we're still expecting that those are on the low side. Another important caveat here is that we used the GLAF sort of unified regional substrate map as our extrapolation layer for going from the sample-wise level up to the lake-wide level. The GLAF substrate is sort of very simplified, has this sort of what I have been calling coarse. They would call that hard, and then these other classes are what I would call fine. But when you really dial in on this map, it's very coarse. It's probably not particularly accurate when it comes down to sort of the transect level of summary or extrapolation. However, we're working very hard to improve that situation right now. And in the next session, or I'm sorry, in the next presentation, you're going to hear about efforts to use the 2-meter and 3-meter LiDAR data that give us really good spatially referenced elevation information, and how we're using those to predict the same coarse versus fine class membership. So our hope is that we can actually improve our extrapolation accuracy in the future by bringing in much better information about substrate. Finally, while I would love to claim that our YOLO algorithm is finding only round gobies all the time, in fact, we're also finding sculpins. We're also finding trout perch. And so right now, we're essentially in the QA/QC effort for our publishing process to verify the exact quantitative rates of misclassification. However, some small slice of that biomass that I showed you is coming from these other critters. However, my co-author Chuck Medengen published this paper where he's showing sort of from bottom trawl evidence relatively constrained ranges of round gobies during the summer season. It shows slimy sculpins beginning to intragrade in the sort of 20 to 50 meter zone, but at really low abundances if you look at those y-axes. So we don't believe this is a massive number. Round gobies are highly dominant in the 0 to 50 zone, but we do believe that it is a factor to be corrected for. So with that, we're very much in the dissemination phase of this research, and I've been starting to talk to folks on the predator-prey working group in Lake Michigan, and I'm really interested to talk to the folks at the QFC and anyone else working on lake trout, for instance, about getting our data into use to improve our understanding of the lake's capacities to support predators. I also believe that with sort of the initial estimates of efficiency we have and some other studies we've been doing on the side about avoidance, that we could begin to sort of scenario build about what the total abundance of round goby is to account for some of these biases that we've already identified. And we could also begin to think about production modeling and measurement. You'll be hearing in the next talk about how we're expanding substrate modeling to improve extrapolation accuracy. Machine learning is getting better all the time. I do believe we will arrive at a solution of multi-species discrimination on the lake bed, which would open this method up to be not just a round goby survey, but to be a fish community survey, especially for the fishes that aren't moving, like highly mobile and moving away from the AUV. This might require better image resolution, but we will find out. And I'm very interested, and my team is very ready and willing to continue the time series and to really, create a new index that could support decision making. So with that, I'd like to point to a huge group of collaborators and contributors, and thank them, and open the floor for questions.